Okay.
So projectile motion, basically we want to figure out if I shoot something or throw something, how far away from me will it go, how high up it got to, time in the air, all that stuff. And its application of the kinematic equations. So the kinematic equation, just to remind you, if I consider the ground at, well, we'll call it y equals 0, y going upwards, and x going over to the right along the ground, well, around the level ground, then y at any time would be the initial y position. I'll call that y sub 0, plus the initial velocity in the y direction times time, minus 1/2 gt squared. This is plus 1/2 the acceleration in the y direction times time squared. And then x at any time would be the initial x position plus the initial velocity in the x direction times time. And then if there was a constant acceleration in the x direction, you would have a 1/2 acceleration in the x direction times time squared. But for projectile motion, we are going to assume that the only acceleration is that due to gravity. That ignores air resistance. You can't handle that in this class, okay? So we are going to ignore any acceleration in the x direction and assume that the only acceleration, which we'll see later on, is related to the force, is due to gravity. Okay, so the only force on this would be gravity while it's in the air. So we're not worried about while it's being shot up or anything like that. We're worried once it's in the air, what's it going to do? And so we're going to use these two equations and see what happens. So the first type of problem, and I'll give a concrete example with numbers. Imagine you have a person and they're shooting a rifle. Rifles are hard to. And the bullet starts out horizontally, and so it's all in the x direction. And let's say that it's 500 meters per second is the initial speed. So about 1800 FPS, something like that. All right, let's say that the initial height of this that it's fired from above the ground is, let's say it's 1.5 meters. Let's see if we can find how far it travels before it hits the ground. How far does bullet travel before it hits the ground? Question mark. And so what we could do is just apply the kinematic equations to this. The time in the air before it hits the ground, that's going to be determined by the y equation. Because when it hits the ground, y is 0. That's the condition. Now I'm going to call this h, and I'm going to do everything algebraically, and we're going to plug in numbers right at the end, okay?
We are assuming he's firing
Horizontally.
0 degrees of elevation and the earth is flat the entire distance.
Yes.
Okay.
These are big assumptions, but we can adjust those if we need to, and we will later. Okay? So let's go ahead and do this. When it hits the ground, y of t equals 0 at ground. So I'm just going to plug in, this is 0. I'm going to call the ground y equals 0. So that means to figure out the time that it hits the ground, I'm going to write 0 for this y of t. What's the y naught, the initial y position? I'm going to call that a. What's the initial velocity in the y direction if it's fired horizontally? Is that in the y direction?
No.
The
Zero.
part of the velocity in the y direction is 0. So this is 0 because it's fired horizontally. I'm not going to write that there. So y equals 0, y naught is h, v naught y equals 0. And so I'd get that the y kinematic equation would be this. Okay? I can solve this for time, and that'd be the time that it hits the ground. So I could write this as 1/2, adding this term 1/2 gt squared to both sides. You get 1/2 g t squared is equal to h. Follow that? Multiplied by 2 over g. This 2 would cancel here, that t with this. So t squared is 2h over g. Take square root and take the positive time. T is square root of 2h over g. By the way, that's the same amount of time as if I just dropped this. So it's strange, if I fire a rifle at, like 1,000 miles an hour, horizontally, it'll be in the air for the same amount of time as if I just dropped the pebble from that height. On the other hand, it'll travel, it takes like a second to hit the ground, it'll travel 1,000, it'll travel like a kilometer or something like that. So, that's, but it's in the air for the same amount of time. You may not believe that, but it's true. All right, now we wanted to figure out how far it traveled. Now, how far it traveled will be the distance it moved in the x direction. I'm going to call that this x naught is equal to 0, and then where it hits, it'll be what I'm interested in. So the x, I'm going to call this actually r for the range. So if I look at the x equation, I plug in r is initial velocity in the x direction, that's v naught, times time, which would be the square root of 2h over g, because that's the time it's in the air for. And this would be my range.
And, oh,
Now, does somebody want to go ahead and plug in numbers for this?
I think time is 0.55 seconds, and the range is 277 meters, I believe.
77 meters. All right, so close to 3 football fields, fired horizontal. You add just a little elevation, you get a lot further. Okay. Let's go examine elevation now. How about that? What happens if we fire it from an angle? So we're going to look at a slightly different problem. And then we'll do one more after that. By the way, I don't want you to memorize these equations. I'd just like you guys to see, how to apply those kinematic equations. Where we look at what conditions we want to meet with these kinematic equations and just start plugging in numbers based on the problem. Okay, so it's all about understanding the problem and then figuring out what to plug into these kinematic equations and how to go from there. So, let's suppose that I have a projectile that is fired exactly from ground level. So maybe you dug a mortar or something into the ground and you're firing up from there. At some initial speed, v naught, I'll say that vector is v naught, and it's at some angle with respect to the horizontal of theta. So maybe we can say, give it specific numbers. We could say that the magnitude of this v naught vector, there's the initial speed, let's say 1,000 meters per second again, or 1,000 meters per second again. And let's say that this angle is 60 degrees. Okay. The question is how this projectile will go up, come back down. What's the range, the distance the projectile traveled before it hit the ground? So R question mark is my question. Well, once again, what we're going to do, we are going to solve for the time it was in the air from the y equation, plug that into the x equation, and get the range from that. Does that make sense?
Can you say again?
So find the time that it was in the air from the y equation. Take that time, plug it into the x equation, get the range. So the x, if I call this x equals 0, then when it hits the ground, this would be x equals the range. Okay, so if I plug in the time where it hits the ground into the x equation, I get that x position being the range. Does that make sense? All right, that's the key step here. So let's go ahead and do that. So from y equation, so if I fire it from the ground, what's the initial y position?
0.
Okay. Now if I fire it with an initial speed of at an angle of theta, what's the initial velocity in the y direction? So if I draw this initial velocity vector, it looks something like this. At an angle of theta, how much of that's in the y direction?
V naught sine theta.
That's right. You're interested in this part of the v naught vector. So I take, so if I call the magnitude of this v naught, then v naught, and this would be v naught sine of theta, and then this would be v naught e sub 0 cosine of theta, like that, okay? So the part of the velocity in the y direction, v naught sine of this angle. That's a key, that's the tricky part, I guess. Sine of theta. Go ahead and plug that into the y equation. If I'm interested when it hits the ground, what do I want y of t to be? 0. Okay, so I say 0 is equal to 0 y naught plus v naught sine of theta t minus 1 half d t squared. I don't have to keep around this 0, it's just, you know, we will say that this 0 is equal to that. And I want to solve for the time. The first thing I can notice is I can divide through by 1 time. So I can divide each term by 1 time. 0 divided by time still 0. Sine of theta, these two t's cancel. This t cancels as one of those. Add 1/2 gt to both sides of the equation. So I would get 1/2 VT is equal to V naught sine of theta. Multiply both sides of that equation by 2 over V. That'll cancel this V and this, and I'm left with the time here. If I do that, that means my time in the air would be 2 over G V naught sine of the angle. Make sense? Let's go plug that into the x equation to get range. X of t, when I plug in that time, is the range if x naught is 0. Okay? So my x equation becomes that range is equal to v naught x, that's the v naught cosine of theta, times the time, which is right up there. So 2 over g v naught sine of theta. So then I need to combine these things. I can, this v naught times this v naught gives me a v naught squared, 2 here, so I get a 2 v naught squared cosine theta sine of theta all over g. And that's my formula for range when I fire at some angle from the ground level. So in this particular case, what would that range be? Cosine theta is 1/2, sine of theta is square root of 3 over 2. Plug those things into here, what would I get? So 2 v naught squared cosine theta sine theta divided by v, which is 9.8. What do I get?
We're using 9.8 as a
Yeah. Yeah, what's the answer?
I got 88,350.
88,350.
Yeah, time is 176.7 seconds.
You said this was what?
176.7, I believe.
Did everyone get that?
I got 88.4 meters.
88.
38.
88, what, did you plug in the V naught squared, not just V naught?
Nope.
That's probably right. I think that's right. So that's 88,350 meters. So 1,000 meters per second, that's actually a pretty serious additional velocity.
Yeah, like that's per second.
Yeah. And so that's, imagine no air resistance, fired at high elevation. That's great. And that's why you can fire big cannons almost that far. They're not affected by air resistance as much as little ones, especially. What's that?
16-inch shell weighs as much as a dragon.
Yeah, well, yeah, no, they are huge, aren't they? They don't have those except on the bevel. They don't make it.
They miniaturize everything.
Yeah. Well, you know what's interesting? They actually have an artillery deliverable nuclear weapon that they developed. And you can see some of the footage from that. If you decide to YouTube it. And they just took a big howitzer and they put they made a little nuclear, the shell was a nuclear bomb. They get it far enough away that it, it's reasonably safe. Somebody, there's a person who once developed a nuclear hand grenade, or the plans for it, but that was a bad idea. There's no way a person could possibly throw it far enough to not die.
What was time on that again? Do you know?
Like 177 seconds.
Yeah. 176.6.
Almost 3 minutes.
Okay.
And the next level, and unfortunately probably the highest level of complexity, is when we fire it from a height at an angle. So we fired it from a height at no angle, we fired it from ground level at an angle. Now let's do it from a height at an angle. And unfortunately this makes it necessary to use a quadratic formula. But this will be what you'll be using in the lab next week. So let's suppose that I have a table, and I have a cannon that's elevated, or a little cannon, so that it fires the ball at an initial speed. Let's do something pretty small here, maybe 3 meters per second, at an angle of 30 degrees with respect to the horizontal. And let's say that the initial height of the projectile when it's fired is 1.3 meters. And this projectile will come over and hit over here. Let's say the distance, let's call the range, once again, the distance from its initial X position to its where it hit the ground. Okay? Let's go ahead and see if we can solve it. So first of all, we're going to want v naught y and v naught x. So if I were to draw that initial velocity, I'm going to call it v naught. So the magnitude of this is just v naught without the vector. It's at 30 degrees. The initial speed would be, or if I call it theta, that'd just be v naught cosine theta down here, and v naught sine of theta over here. That's the same as. So this would be v naught at y, this would be the initial velocity in the x direction, v naught x. Follow? All right. So what's the rule? What should I do if I want to figure out this range? Well, what have we done the past 2 times? What's the logic?
Figure out the time.
With the y.
Y is 0.
That's right. We figure out the time where the y is 0, and then plug it in the x equation.
Yeah.
So let's go ahead and do that.
So why not going to be 0 here too?
No.
Well, I'm going to call this h. The initial y position, I'm now firing it from a height, h.
Okay.
I'm going to call this y equals 0 down here. By the way, if I called this y equals 0 up here, this would be y equals negative h. I'm going to end up getting the same equation. It won't matter. As long as I'm consistent throughout the problem. So I'm going to say that y naught is h, and then plug things into here. So if I'm interested when it hits the ground, I'm interested when y of t is 0.
Mm-hmm.
I'm going to say 0
H.
is equal to h plus the initial velocity in the y direction t times time minus 1/2 g t squared. And I want to figure out, I want to solve for that time. Now, unfortunately, this has a term without the t, a term proportional to t, a term proportional to t squared. So there's no way, like before, what we did last time was we divided through by the t. I can't do that with this term here and make it any simpler. So this is a quadratic equation for time. Okay, simply form 0 is equal to c plus b times t plus a times t squared. In that form. So what's the quadratic formula?
Plus or minus b, or b plus.
Yeah, so t would be negative b plus or minus the square root of b squared minus 4ac all over a. So I'm going to go over and I'm going to compare what a, b, and c are for this formula. So t is, well, b is b naught sine of theta, right?
Mm-hmm.
So negative b naught sine of theta plus or minus the square root of b squared, so this thing squared, minus 4 times a, which is negative 2d8, negative 1/2 g, sorry, times c, which is h. So it's minus 4ac all over 2a, which is 2 times minus 1/2 g. All right, let's simplify this.